Okay, let's have a look at a few past paper questions. So the line 3y plus x plus k is the normal of the curve. I reckon I did this question for you in the previous exercise, but we'll do it again. Is a normal, so this is the normal curve, normal to the curve y equals x to the 5 at x equal to -1. So first things first, let's work out the gradient of this normal line. So the normal line is given by 3y is equal to minus x minus k, y is equal to minus x on 3 minus k on 3. So the gradient of the normal is equal to minus 1/3. Now that's going to be the same as the gradient of this line at that point. So dy dx is equal to 5x to the 4 plus b. Now at x equal to -1, dy dx is equal to 5 times -1 to the 4 plus b, which is equal to 5 plus b. Now that has to equal, that's the gradient of the tangent, isn't it, at that point there? So the gradient of my tangent mt has to be equal to -1 over minus 1/3, which is equal to 3. So that 5 plus b has to be equal to 3. So b is equal to -2. All right. So remember, the derivative gives me the gradient of the tangent line everywhere. So I've now got y equals x to the 5 minus 2x. So there's a start. And at x equal to -1, okay, what's y equal? At x equal to -1, y will equal -1 to the 5 minus 2 times -1, which is -1 plus 2, which is equal to 1. So our curve goes through the point -1, 1. My tangent line and normal line have to go through the same point. So for normal, it also has to go through the point -1, 1, which means 3 times y, which is 1, plus x, which is -1, plus k has to equal 0. So 3 minus 1 plus k is equal to 0. 2 plus k equals 0. K equals -2. All right. Let's keep moving along. The graph, the left is a graph of, we'll take that as f dash of x, we will. So looking at the graph here, at those points there, f dash of x is equal to 0. Yeah, I really think I've done these. Is equal to 0. So I have turning points along here at x equal to -1 and y, whoops, and x equal to 3. So the gradient here is above the axis. So this section here is where the gradient is positive. Okay. This section here, that's where the gradient is negative. And as we said, those points there, that's where the gradient is 0. So gradient is positive to the left of -1. So the gradient is positive to the left of -1. So to the left of -1, I have a positive gradient. So maybe it looks a little bit like that. Okay, we get to -1 and we're at 0. In between -1 and 3, my gradient is negative. So it's coming down at some point in time. Okay, it's down the whole way. So the gradient is negative through there. And then outside of this section here, my gradient is positive again, so it's heading up. So the graph could look like that. The actual coordinates of these turning points are unknown. Okay, we're not too sure. We can't work those out. All right. Part B, find the values of x for which the g of x is an increasing function. So that means whereabouts is g dashed of x greater than 0. All right. So g dashed of x is equal to 3x squared minus 18x plus 15. 3 at the front, x squared minus 6x plus 5. Hopefully that factorizes. Oh, what's that? Minus 1 minus 5, isn't it? X minus 1, x minus 5. Negative 1 times negative 5 is positive 5. Negative 1 plus negative 5 is negative 6. So a quick graph of the derivative function gives me intercepts at 1 and 5. It's a positive parabola. So that's the derivative. Okay. So whereabouts is the derivative greater than 0? So the derivative is greater than 0 there and there. So that section and that section. So therefore, g of x is increasing at minus infinity to 1, round bracket, because at 1 the gradient is 0, and 5 to positive infinity. Okay? Let's have a look. Okay, final graph. Let's get a pen. The graph of f of x is given by there, where x is an element of R, I think that says. Some of my symbols don't come out. Sketch on the same set of axes the graph of the function of f dash of x. Okay, so first things first, whereabouts? So here the gradient is 0 up to that point there. So the gradient is 0. All right. Now at negative 1, the derivative is not defined because we have that cusp. Okay, so the gradient is not defined there. The derivative is not defined there either. So let's have a look at this section of the graph here. We've got a straight line with a constant gradient. Now, all I know is we don't exactly know how high it gets. It's got a run of 3 and it rises a certain amount. So it's a positive gradient. What it exactly is, I don't know. So let's just get rid of that so we don't get confused. So I've got a positive gradient. It's not defined there because it's not defined at negative 1. And it's not defined there at 2 because our graph is not continuous. Okay. Now here we've got a parabolic graph, or we'll call it parabola. So it should be an increasing function. It's a positive gradient. So it looks like a turning point there. So it starts at 2. So let's go a different color. And maybe, again, it's undefined. And we might go something off like that. Okay. So key points are where the derivative are not defined. Okay. Which is, so f dash of x doesn't exist at x equal to negative 1 or x equal to 2. All right. What is the domain of the function of y equals f dash of x? Oh, well, there we go. So assuming that that's R there, the domain is equal to R excluding negative 1 and 2. All right, job done. Next page. Right, velocity in meters per second of a particle moving is given by, sketch the graph of the velocity time function, clearly label any endpoints. I'll just think, I'm assuming that's a t is greater than 0 there. So we've got 10 over t plus 2 plus 1. So it's a hyperbola, yeah, shifted 2 units where to the left, because it's a plus 2. So I've got an asymptote at -2, 1 unit up. And so it's going to be something like that. Yeah, and something like that. So that's what it looks like. But let's think about, we're only sketching it for t greater than 0. So let's put our hyperbola in, sorry, our asymptote in, and that's going to be the line of v of t equaling 1. We're going to have a v-intercept, so at t equal to 0, v of 0 is equal to 1 plus 10 over 0 plus 2, which is equal to 6. So I'll put 6 there, and our graph is going to approach the line there. Sketch the graph of the velocity time graph on the axis. Label clearly any endpoints or asymptotes. So let's get the point 0, 6 labelled. And we've got the asymptote labelled. Okay, so job done. Find the values of t for which the velocity of the particle is less than 3 meters per second. So I've got to solve 1 plus 10 over t plus 2 to be less than 3. Take the 1 over. 10 over t plus 2 is less than 2. So multiply. So we'll have 10 is less than 2 times t plus 2. Bring the t back, the 2 back. 5 is less than t plus 2. 5 on 2 is less than, oh, geez, what am I doing? Subtract 2. And subtract 2, and I get 3 is less than t. So we're saying the velocity of the particle, therefore, velocity is less than 3 for t greater than 3 seconds. Okay. Find the distance travelled by the particle in the first second. Okay. We're probably not quite ready to do this one, boys, to be honest. If I want to get, just to briefly explain, if x is equal to whatever it is, and dx dt is equal to the velocity, well, to get a position equation, I've got to take the antiderivative of dx dt. Okay, so what that means is I actually have to anti-differentiate 1 plus 10 over t plus 2 dt. And if I anti-differentiate that, I'm going to get 10 plus 10 natural log t plus 2 plus some constant. Okay, so that's what my position is equal to. Now, we're not ready for that yet. That's second semester, or unit 4, I should say. So I don't want to go into any anti-differentiation, but I'm not fobbing you off. But yeah, let's leave that one go for next term. What have we got here? Point AB, positive real numbers, y equals 2x minus 5. That looks reasonable. Let S be the distance from the origin O to the point P. Find the distance S in terms of A. So what is the distance between 2 points? Okay, these are good questions because the distance between 2 points is really just Pythagoras' theorem, isn't it? So it's that distance there squared plus that distance there squared. So my distance formula is actually given by the square root of, and it could be on our formula sheet, y2 minus y1 squared plus x2 minus x1 squared. So the distance is equal to the square root of the y values. So it's b minus 0 squared plus a minus 0 squared, which is just the square root of b squared plus a squared. But it says this in terms of a only, and I've got b there. So the trick is to remember that b value there is just my y value. And I've got an equation up here that says y is equal to 5 minus 2x. So if x is equal to a, y is equal to 5 minus 2a. So this coordinate up here, P, that's the coordinate A, 5 minus 2a. So in actual fact, B is equal to 5 minus 2a because B is my y value. So I can change this to be the square root of b squared, which is 5 minus 2a squared plus a squared. I could leave it there, but I'm going to use calculus and it's tech-free, so I'm probably going to need to simplify, which is equal to the square root of 25 minus 2 times a times b, which is 10 20a plus a squared plus another a squared. So I'm going to put the distance s is equal to the square root of 2, oh, that's a 4a squared, nearly a bad mistake, wasn't it? We're going to write 5a squared minus 20a plus 25. So look, I could take a square root of 5 out the front, but I might just leave it like that. Using calculus, the minimum value. Okay, so the minimum occurs at ds dA. So don't forget that that's the same as saying s is equal to 5a squared minus 20a plus 25 to the power of a half. So dsdA is equal to, a half comes out the front, don't change anything else, minus 20a plus 25 to the minus a half times the derivative of inside, which is 10a minus 20. So let's simplify that, and I get 10a minus 20 over 2 times the square root of 5a squared minus 20a plus 25. Now I need to solve that equal to 0. So if I just maybe take 10 out as a factor, I can go a minus 2 over 2 5a squared minus 20a plus 25. Now I've got to solve that equal to 0. Now with any fraction, this expression can only equal to 0 if the numerator is equal to 0, because the denominator is not allowed to be 0. And for that to happen, therefore I get, if you like, 10a minus 2 is equal to 0. Therefore, a equal to 2 is where the minimum occurs. So that's the minimum value. So at a equal to 2, I've got to work out what s is equal to. So where's s? There's my rule for s. A equal to 2 is the minimum. So s is equal to the square root of 5 times 2 squared, which is 4, minus 20 times 2 plus 25 of 20 minus 40 plus 25, which is equal to the square root of 5. So the minimum value of s, therefore, minimum value of s is root 5. Do we have units? No. At a equal to 2. All right, so that little statement there just makes sure examiners and markers know where to find your answers.